Hey, what's up? It's your old pal, Mr. Cook. We are working on this Unit 4 Part 2 test review. So in the first video that I made, we went over identifying which method to use to integrate or to take the antiderivative. And then we went through all the different methods to find the antiderivatives. And then this is my last video that I'm making. This is the one going over how to work with improper integrals. So the first step is to take the antiderivative, obviously. And then after that, you need to evaluate it using limits, because usually when we do a definite integral, we're allowed to use the fundamental theorem of calculus and then evaluate those antiderivatives, like the integrals, just using like constant terms, and adding them together or subtracting them in the case of the fundamental theorem. But with improper integrals, we're using infinite values, and that can cause some issues. Or we're evaluating it at like an asymptotic value, and that can cause some problems as well. And since we have the potential to be using infinities, we want to handle it with care, and that's why we use limits and tread lightly as we're finding potentially some answer. So it's really helpful to know a couple of like limits, like just memorize them. In general in this class, I think it's a good idea. Ones like this, like if you have a rational function, if you have a limit and then it becomes something like this, 1 over 0 or 0 over 1 or 1 over infinity or infinity over 1, like these all become specific things. Like if you get some number over 0, that's bad news. That basically goes to infinity, and you get like a DNE kind of situation there, okay? Because it could be infinity or it could be negative infinity, depending. So, you don't want to work with that one. So you get a DNE. With 0 over 1, that's okay. That just goes to 0. With 1 over infinity, this also basically goes to 0. Same thing with negative infinity. Infinity over 1, positive infinity or negative infinity, or over any number, I guess, for either of these cases. This still goes to infinity or negative infinity. So you're going to want to say that that's a DNE situation as well. And then you also have these other weird cases like natural logs. So if you have the natural log of 0, the natural log of e, the natural log of 1, and the natural log of infinity, you want to tread lightly with those, okay? Because with the natural log of 0, this basically goes to like negative infinity, which would be a DNE situation for a limit. The natural log of e is a special case. It just becomes 1. That's it, just 1. Natural log of 1 is going to be 0. And the natural log of infinity does indeed go to positive infinity, which would be another DNE kind of situation. And then the last thing you want to watch out for are the exponential functions. So e or some base to the 0 power, e to a base of 1, or sorry, e to a power of 1, e to an infinity power, and e to a negative infinity power. Okay, so if you have e to the power of 0, that just goes to 1. E or something to the power of 1 just goes to the base, so e in this case. E to the infinity power goes to infinity, so that's a DNE situation. And here's a weird one. E to the negative infinity would be 1 over e to the infinity, which become 1 over infinity, which goes to 0. So this thing actually goes to 0. So watch out for these DNE situations, when you're handling these limits. So here's the deal. If you perform an improper integral and one of your bounds that you use during with the fundamental theorem of calculus, if it ends up with an infinity or like any of these DNE situations, any of them, then what happens is that you cannot proceed with your improper integral. You got to stop there. When it's one of these cases, then we say that the improper integral diverges, or it doesn't go to a single value. It just keeps going infinitely, or it oscillates back and forth between values or whatever. It diverges, and that's bad news. So watch out for these cases. We're going to see them kind of regularly as we go through the improper integral problems. Okay, so anyways, starting off with our first improper integral problem, number 6. So when we did the antiderivative for this thing, we ended up with the following. We had -1 over natural log. So like, the indefinite integral of 1 over x natural log of x squared dx, this becomes -1 over the natural log of x plus our constant c. But if I were to apply like a definite integral, it's a little bit different. So let's keep this in mind. Let's remember that this is what the antiderivative is. So let's evaluate this improper integral. So I start off with writing it out, 3 to infinity, and that's how you know it's an improper integral. By the way, it goes to infinity, or it has some problem with the domain. And there aren't any problems with the domain because here's where you could have problems: division by 0. But the only way you get division by 0 is if like x is equal to 0, or if x is equal to 1 from that one. So x is not allowed to be equal to 1 or 0. And on top of that, x actually has to be a positive number only, because if you're using natural log only uses numbers that are greater than 0 in general. But luckily, like, neither of those are part of the boundary, because if I go from 3 to infinity, that excludes those numbers. So I don't have to worry about them. But it's always something that you want to consider. What domain restrictions do I have? Is that part of my bounds? Okay, so next up, after we do this, immediately after, since we can't evaluate a definite integral with infinities, we've got to use limits. So we're going to say that we're going to use the limit as some value, and it doesn't matter what it is. You call it H or B or A or a hamburger emoji, whatever you want. You can take the place of that infinity. So I'm just going to use B. So I'm going to say B is going to go to infinity, and then I'll rewrite it 3 to B, and then my antiderivative x, natural log of x, quantity squared dx. Now I already know what the antiderivative of this is going to be, so then I'd write that out next. So I still have my limit on it. I have the limit symbol and this limit notation all the way up until I evaluate the limit. So this the integral, this antiderivative is going to be -1 over natural log of x, and then I'm evaluating this thing from 3 to b. So now I use fundamental theorem, plug those values in, and I get the limit as b goes to infinity of -b over natural log of b, and then minus -1 over natural log of 3. Oh wait, why did I put a b there? My bad. That should be a -1. Sorry. Okay, now I'm gonna evaluate my limit. So the first one, this is just a constant. The second one, so I don't really have to worry about that. But this limit right over here, I do need to evaluate. So what I would do is I just draw a little arrow. I'd box this and put a little arrow around it, and then I'd say hey, there's an issue here, because basically this becomes -1 over the natural log of infinity. So it's so basically this becomes -1 over the limit as b goes to infinity of natural log of b. And we just talked about this earlier. As if I have the natural log of infinity, that becomes infinity. So this goes to -1 over infinity. And -1 over infinity is basically the same thing as 0. So this whole thing just becomes 0. So that's really good. So once I evaluate that limit, here's what this all becomes. So now I'm going to write over here equals, or I can do it off to the side here, equals. So it's going to be 0. That whole thing becomes 0. And then this becomes a +1 over natural log of 3, because the negative and the negative make a positive. And that's my number. So I just get 1 over natural log of 3. So this thing does converge, and this is what it converges to. Okay. And by the way, I guess I didn't say this earlier. If a limit does exist, in other words, you don't have any of these issues with DNE, right? So no divergence, then we say that it converges and it goes to one specific value. So that's number 6. Now moving on, the next improper integral is going to be here at number 15. So it doesn't look like it's improper based off of just a first glance, because there's no infinities, but take a look at the domain. So x is not allowed to be equal to 2, and 2 is smack dab in the middle of that boundary between 1 and 3. So when you have an improper integral and you have an asymptote in the middle of the boundary, you need to split it into 2 separate integrals when you're working on it. So in an earlier video, we had done the antiderivative for this. So if I just look at the indefinite integral, 2 over x minus 2 dx, we got an antiderivative of 2 times the natural log of the absolute value of x minus 2 plus c. So I'm going to use that here in a little bit. So let's set this thing up first. So let's use the improper integral. So we have integral from 1 to 3 of 2 over x minus 2 dx. And so then I need to rewrite this thing using my limits. So since 2 happens, I need to split this up into 2 separate integrals. One's going to look like this, 1 to 2, 2 over x minus 2, and then dx. And then the other one is going to go from 2 to 3, so finish the entire boundary, 2 over x minus 2 dx. Okay, so let's rewrite this using limits. So I'll just use like b again. So the limit as b goes to 2 of integral 1 to b 2 over x minus 2 dx plus, and then I'll use the limit again, limit as b goes to 2 of, let's see, b to 3 of 2 over x minus 2 dx. And I already did the antiderivative for these ones, so that's this thing here. So I get limit as b goes to 2 of 2 natural log absolute value of x minus 2. And then I'm evaluating this from 1 to b. And then the other one is going to be limit as b goes to 2 of, same thing, 2 times the natural log absolute value of x minus 2. But I'm evaluating this one from b to 3. Okay, now we use the fundamental theorem of calculus and plug those values in. So we've got the limit as b goes to 2 of 2 natural log absolute value of b minus 2 plus, or sorry, minus, my bad, minus 2 natural log absolute value of, I'll plug the 1 in, 1 minus 2. Now the plus comes in from there. And then it's going to be the limit as b goes to 2 of, and then if I plug in the 3 there, I get 2 natural log absolute value of 3 minus 2 minus 2 natural log absolute value of b minus 2. Okay, so now let's start evaluating these limits. Well, I'm just going to evaluate this first one here with b going to 2 for this. So this is what I get. I get, if I evaluate this, then I get 2 natural log absolute value of 0. And that's bad news, right? Because the absolute value of 0 is going to be infinity. So this thing goes to negative infinity, and that means it's a DNE situation. So guess what? Even though I have all these other things to do and another limit entirely to take, I can just stop right there, because if this thing goes to negative infinity, I'm done. This thing is divergent, and I can't go any further. So if you end up with an infinity or a negative infinity, just stop right there and say this thing is divergent. So that's number 15. Okay, the next improper integral that we have is number 21. So when we worked on this in an earlier video, we found out that the antiderivative for this thing is going to be 5/4 x minus 1 to the 4/5 power plus c. But, we're not going to need that in a little bit. Okay, so next I would look and see if this is going to be an improper integral, obviously, and it is, because I'm not allowed to use 1 in the denominator, because if I do that, that's bad news. So if that's smack dab in the middle of it, I've got to split this integral apart and then use the limits from there. Okay, let me save some space by writing up a bit higher. So 0 to 5 of 1 over quantity x minus 1 to the 1/5 dx. So I'd split that apart. It'd go from 0 to 1. And then from 1 to 5. Okay, and then we'll rewrite this with our little limits. So limit as, and let's use b again, b goes to 1, 0 to b, and then from b to 5. Or, well, I'll write it again. Limit as b goes to 1 of b of 5. Okay, so we already did our antiderivative, and we know what it's going to end up being, so we'll rewrite that. So limit as b goes to 1 of 5/4 x minus 1 to the 4/5 power. We're evaluating it from 0 to b. And then also we're doing b goes to 1 for the same thing, 5/4 x minus 1 to the 4/5. Now we're evaluating it from b to 5. Okay, so now let's plug in using fundamental theorem of calculus. We get limit as b goes to 1 of 5/4 and then b minus 1 to the 4/5 power minus 5/4 0 minus 1 to the 4/5 power plus limit as b goes to 1. And I really should put parentheses around this when I'm doing more than one. So even when I go back to like this one, I really should have had parentheses around this now that I think about it. Because the b for this is actually going into like this b as well. And it's not immediately apparent by looking at it. So make sure to put parentheses around them. I should have put it around here as well. Anyways, okay, so parentheses around this part. And then this limit as b goes to 1, I'm going to put that here as well. So I have 5/4 and then 5 minus 1 to the 4/5 minus 5/4 b minus 1 to the 4/5. Okay, now if we evaluate the limits, if I do plug in 1 over here, I get 0. 0 to the 4/5 is just 0. So this limit right here just becomes 0. So 0 minus 5/4, 0 minus 1 is negative 1 to the 4/5. And then plus this thing, that's going to be 5 minus 1, so 4. So that'd be 5/4 times 4 to the 4/5. But then now if I plug in b over here, that's a 1. 1 minus 1 is 0. And again, 0 to the 4/5 is 0. So that becomes a 0 as well. And that means that this thing does converge. And this is what it turns into, whatever all that stuff adds up to. I don't really care what it actually does add up to, but you know that's your answer right there. Okay, that's number 21. 27 is next. So this one, you're not allowed to use 0 for your denominator, but it doesn't really matter. That's not part of the boundary, so we don't care. The only thing that matters is then infinity. So this is good. We're not going to have to split this one apart. It's just going to be evaluating at the endpoint at infinity. So we did this problem a little bit earlier as well. We ended up with negative 2/3 x to the 3/2 power, negative 3/2 power, sorry. So I'm going to use that for my antiderivative. Now it's just kind of about like writing up the formalities and stuff. So integral 4 to infinity of x over x to the 7/2 dx. So I'm going to rewrite this using a limit as b goes to infinity of 4 to b, and then x over x to the 7/2 dx. When I do the antiderivative of this thing, you know, I already know what that's going to end up being. So I get limit as b goes to infinity of negative 2/3 x to the negative 3/2 power. I'm going to rewrite that real quick because if I have a negative exponent, I'll just put it in the denominator. So like negative 2/3 and then 1 over x to the 3/2. And then I'm evaluating this from 4 to b. Okay, so using fundamental theorem now, I'm going to plug those numbers in. So limit as b goes to infinity. If I plug in the b part, I get negative 2/3, 1 over b to the 3/2, and then minus negative 2/3, 1 over 4 to the 3/2 power. So if I evaluate this limit right over here, here's what I basically get. I get like 1 over infinity to the 3/2, right? Which is the same thing as 1 over infinity. And, you know, as we know, 1 over infinity basically just goes down to 0. That's one of those numbers that we have from up above. So here's how I write this up formally. I just like would you know, bunch this together because it's right next to each other. And I'd say this thing goes to 0. Okay. So if that goes to 0, that means that overall this thing is going to be 0 plus 2/3, because I'm combining the negatives there, times 1 over 4 to the 3/2 power. So this does converge to some number, and that's what it ends up being right over here. Okay, that's number 27. 36 is the next one. There we go. All right, so after I did the antiderivative on this thing, here's what I ended up with. I got a 1/2, and then x squared natural log of x squared minus x squared. Okay, so that's what the antiderivative ends up being. All right, now let's check for domain restrictions. So the only domain restriction that I would have is 0 for this, but that's not part of the boundary, so I don't have to worry about it. Okay, so now let's go ahead and do the improper integral for this. The only thing I have to worry about is that infinity. So integral from 3 to infinity of x natural log of x squared dx. So I do my limit as b goes to infinity, integral from 3 to b of x natural log of x squared dx. And then I use my antiderivative, so that's going to be limit as b goes to infinity. And then antiderivative is going to be a 1/2 x squared natural log of x squared minus x squared. Then I'm evaluating this thing from 3 to b. So if I plug in b, I get limit as b goes to infinity of 1/2 parentheses b squared natural log of b squared minus b squared. And then minus, and then if I plug in the 3's, I get 1/2 b squared 3 squared natural log of 3 minus 3 squared. Okay, now if I start to do my my limit on this thing absolutely explodes. So this limit right here, oops, sorry, I cut off the negative b part. There we go. This limit right here, yeah, it like, if you just even look at like the first part, this is going to be infinity squared. So this whole thing just goes to infinity. Basically, you don't even have to do much work for that. It just is going to be gigantic. So this thing goes to infinity, and then the other stuff is just a number. So that means that since it goes to infinity, this is a bad case, right? So we just stop right there, and we say that this is divergent, or diverges. Okay, so that's number 36. That's a pretty easy one, diverges. And then the last of the improper integrals is going to be this one, number 41. So when we did the antiderivative for this one, it was, let's see, negative 1/3 times negative 1, and then 1 minus x to the third to the negative first. So I'm going to make that look a little bit nicer. Let's absorb those negatives. Let's put that in the denominator. There we go. Okay, so there's my antiderivative for this. And oh man, this sucks. So we've got an infinity, and we've also got a domain restriction because x is not allowed to be equal to 1 in this case, and that's part of the boundary. So we got to split this up twice. Split it up into 2 integrals, and then also put a limit on that infinity. So here's how you can do it. We write up 0 to infinity, x squared over 1 minus x to the third quantity squared dx. And then we could split it apart now, I guess. Well, this is a little bit, I'd probably put an arrow there just because I don't like saying equals unless I branch right into the limits. So I'd use an arrow, and then I'd go from 0 to 1 for this, x squared over 1 minus x to the third squared dx. And then add on to that from 1 to infinity of x squared over 1 minus x to the third quantity squared dx. Okay, and then now I'm going to rewrite this using my limits. So I'll use b for the 1, and then I'll use a for the infinity. Okay, so like in the first one, I do the limit as b goes to 1 of 0 to b x squared over 1 minus x to the third squared dx plus, and then I've got the limit of, and then I've got 2 boundaries. So I've got my b at the bottom, and then I'll put a at the top. So as b goes to 1 and a goes to infinity for this thing, x to the second power over 1 minus x to the third quantity squared dx. Okay, and then I know my antiderivative for this, so it's going to get a little bit tedious here, but we're just going to keep writing the steps. So we've got limit as b goes to 1. Antiderivative for that thing is 1 over 3, 1 over 1 minus x to the third. And I'm plugging in from 0 to b. Plus, and then the other one that I'm going to have is limit as both b goes to 1 and a goes to infinity of 1/3, 1 over 1 plus 1 minus x to the third, evaluated from b to a. Okay, and now I use fundamental theorem and plug these values in. So I get, let's see here. So if I plug the b part in first, I get 1/3 1 over 1 minus b to the third minus 1/3 1 over 1 minus 0 to the third plus, oh wait, I gotta put my limit in there too, don't I? Limit as b goes to 1. Sorry about that. Plus limit as b goes to 1 and a goes to infinity of 1/3 1 over 1 minus a to the third minus 1/3 1 over 1 minus b to the third. Okay, let's put parentheses around that. Did I forget to put parentheses around the last limit that I did too? Oh, I guess I didn't have to for that one because it wasn't split. Okay, so now if we plug in the 1 part, right, that's where things start to go pretty crappy. Okay, so even on this very first limit, I get 1/3 and then 1 over 1 minus 1, which is 0. And 1 over 0 goes to infinity. So this thing goes to infinity. And that means it's a DNE situation. And if it's a DNE situation, we just say it diverges. We don't even care what's going on with all the other stuff. So we can just stop right there. Okay, that's it for the improper integrals. That's all of the improper integrals for this worksheet. I hope this was helpful. If not, go seek out your calc teacher, get some help from them. Okay, thank you very much. And that's it for this video series. Talk to you later. Bye-bye.